Okay, so last week we started looking at we started by looking at the iron phase diagram, right? And introduced the basic terminology. We go from, as we go up in temperature, from BCC ferrite to FCC austenite, back to a BCC delta phase before melting. And then we looked at interstitial sites, and we made the observation that in the austenite phase, the interstitial atoms prefer to reside in the octahedral sites, and they stay in the BCC octahedral sites as well because of this asymmetry of that site, and we only need to displace two atoms. Remember, the interstitial sites in BCC are smaller, right? They're still, even the tetrahedral sites, which are larger, are still smaller than the carbon atoms. So energetically, it's easier to push two atoms out of the way to squeeze yourself in than to squeeze four out of the way to squeeze yourself in, even though the volume itself is a little bit bigger. All right, we talked about Luder's band formation and dynamic strain aging as being consequences that since the distortions caused by the interstitials in BCC are very strong tetragonal distortions, that the dislocations tend to align themselves so the interstitials are along the core, right? And this gives a very strong pinning force and effects, but that these interstitials have very high mobility. So in conditions like this, you get strong pinning, and then as the dislocations move in their herky-jerky way, the interstitials catch back up and repin the defects. And this is termed dynamic strain aging. Right? Yeah.
But if you've got that happening with interstitials, would you need a structure that is essentially free of grain boundaries so they can travel through the full matrix to catch up with dislocations?
No, I mean, remember, grains are big compared to the Berger's vector, right? So I mean, so think about how many atoms can actually fit in a big grain and how many slip steps you can make. And if you look at if you consider diffusion as a random walk, right? The distance that the atoms are actually going to travel, right, are fairly small compared to the size, the 20 to 30 microns that a grain has, right? Solid solution hardening, right? Hall-Petch effects, and we said we pointed out again, beryllium has a very high solid solution strengthening effect because of the big size mismatch. Yeah.
So now we have the large effect. Also,
the Hall-Petch?
No, the biggest slide.
So this is.
Not this.
So this?
Yeah. So,
oh, no, there is strain rate effects here. Right? If your strain rate is such that your dislocations are going to go significantly faster than your diffusion, right, you won't see this jaggedness, right? It behaves. Remember, strain rate and temperature have inverse effects. Generally, we can consider that there's some sort of time temperature superposition. So the faster you strain something, it's like deforming it at a colder temperature. Right? So you won't, if you have high rates, you don't see this dynamic strain aging effect. Right? This is all, whenever I talk about mechanical properties, generally I'm talking about quasi-static properties, right? Strain rates of 10 to the minus 3, 10 to the minus 4. Typical tensile test strain rates, unless we say otherwise. Okay, so now we actually get into steel, right? So the iron-carbon phase diagram here. So I assume everyone is at least mildly familiar with this. A couple things to point out, right? So what actually is the equilibrium phase at low temperature? Right. So here we have alpha plus carbon or alpha plus cementite. Right. What's this carbon? What form does the carbon usually take? What's that? It should be, thermodynamically, it is graphite, right? But you don't get there, right? Metastably, you have these carbides, right? So we almost never see graphite except at cast irons, where you're out. So the max here, whenever you're, the classification scheme, I should say, generally, right, if we're under this 2 weight percent, if we're under the max solubility, then we classify it as a steel. If you're out here, it gets classified as a cast iron. And cast irons we'll talk about later at the end of the term. So really, for the most part, for this part of class, we're only concerned about here, mostly in the neighborhood of the eutectoid region here, right? Okay, so what goes on up in this corner here? Right. This is the paratectic point, right? Right. So what is a paratectic? Go back to your phase diagram.
One solid phase to another solid phase.
It's a solid and a liquid phase.
Solid and a liquid to another solid, right? So here you have delta plus liquid going to FCC austenite, right? In the grand scheme of things, not very important, right? Because anything that goes through this paratectic point then has to pass through all the stuff that happens in the eutectoids, right? So basically the history of this paratectic gets washed out by any further processing, right? So we won't spend a lot of time up there. So then we've got cementite, right? So here's our picture of it, and it is again thermodynamically unstable, but very highly metastable. And cementite is also ferromagnetic, right? So this is the primary carbide that we're going to be talking about, right? This is what gives steel its. When we talk about steel being a composite, most of the time we're talking about a composite of ferrite and cementite, right? A two-phase region. But there's a whole bunch of other carbides that are possible. See, at exceptionally low at these lower temperatures for very long times. We get these Hague carbides, right? And there's a whole suite of other possible carbides that can show up. So here's another picture of cementite, and the Hague carbide is here. But again, any of these can appear depending on the composition, right? Don't try and do any memorization. None of those are. None of these are important. Or I mean, memorizing anything is not important. Okay, so if we zoom in a little bit on the region of interest, right? We put two lines on here, right? And any idea why we've got the solid line and the dashed line? On cooling and on heating, right? There's always hysteresis, right? You need some undercooling or overheat to get things to happen, right? At the equilibrium temperature, you don't have any driving force. So the dashed line represents on heating, right? Is the solvus on heating, and the solid line represents on cooling, and the distance between the two is the hysteresis, right? And there's nomenclature that goes with that. There's AC, these points, critical points, and if it's C, it means heating, and if it's R, it means cooling, and E means equilibrium, right? So the critical points are detailed in this way, right? So we'll keep coming back to this, and you should be able to make a simple sketch of at least this part here of this phase diagram, basically from memory, with knowing the key critical points, right? So what's the eutectoid composition? 0.76 at 727C, right? And know the basic shape of these regions, and know, this eutectic here, the eutectoid here, and with that you'll be pretty well set. Okay. So we know what makes steel work is that the solubility of carbon in austenite is so much higher than in ferrite, so that when we cool down, we're going to we have a structural change, and we also have a solubility change. And what makes steel really interesting is there's a whole lot of things that can happen, right? So we can have reconstructive transformations or displacive transformations. So when we say reconstructive, we basically mean anything that's diffusion mediated, right? And displacive means that there's a shear transformation, right? So obviously martensite is a shear transformation, right? And generally the growth of ferrite, with the exception of Widmanstatin and acicular ferrite and bainite. These tend to be diffusive, reconstructive. The growth of perlite is reconstructive. These happen mainly or completely by short range and long range diffusion. But we have a whole bunch of mechanisms that are displacive and mechanical in nature, actual physical shearing of our material. And a key concept that's going to keep coming up is this idea of para-equilibrium nucleation, right? Carbon diffuses much faster than any substitutional atom, right? Because it's interstitial, right? Substitutional diffusion requires a high concentration of vacancies, and the interstitial does not. So the idea here is that at nucleation, the substitutional solutes are too slow to allow to get to the full equilibrium. Basically, the substitutional elements, the composition doesn't change except for the fact that carbon can easily move out. Right, we can see that by looking at the diffusivities. Right, if we look into ferrite, we've got 4 or 5 orders of magnitude difference with respect to the diffusion coefficients at the temperature range that we're interested in. Right. So carbon, substitutional alloys, these are like getting on, hanging a bunch of hippies in a minibus for a road trip, right? Meandering across the country, right? It takes a long time, and there's a lot of things that has to happen and a lot of logistics, right? Whereas the carbon and the nitrogen is getting on a plane, right, and flying, right, much faster, much more efficient. Okay, so let's consider what's going to happen. Right, so this got shifted a little bit. So if we're right at the eutectoid composition, what's our structure going to look like? Right, and we cool down, and we cool down very slowly. Right, so we're going from gamma, so our carbon is fully soluble. We come down exactly through the eutectoid point. So now we have alpha that has a fairly low solubility, a virtually zero solubility of carbon, and our cementite. Right? What's this structure look like? Coarse, yeah, so 100% basically coarse perlite. Right? What about if we are hypoeutectic? Right? If we have our hypoeutectoid, right? What if we have less carbon? What do we get?
We'll have ferrite along the austenitic grain boundaries, and then the remainder transforms into perlite.
That could happen depending on the heating, right? We can also get equiaxed ferrite grains surrounded by perlite, depending on what else is in there. But you're right. We're going to have a mix of ferrite and perlite depending on where we are and what's done to it after. Right? What about if we're hyper? Right? Right, what's going to happen? but come down into the two-phase region. So now we've got austenite and cementite, right? So we're going to nucleate cementite, and then we're going to come here, right? So now we're going to have what kind of structure? Cementite and perlite, right? So this is just sort of a preview. If we're real close to eutectoid, we get full, nice, clean perlite. If we're hypo, we get a mixture of ferrite and perlite. Right. As we, depending on what our heat treatment is, or how our cooling, our exact cooling schedule, we can get a whole bunch of stuff, right? So we have Widmanstatin type, these long needles of plates of ferrite, right? We can have grain boundary allotropomorphs, idiomorphic ferrite, which forms these bits of ferrite that are inside of the grain, and then we can have cementite that grows in a Widmanstatin as well. It's hard. It takes an eye to get used to seeing these things because a lot of features in steel look alike under optical microscopy, especially like trying to tell the difference between bainite and martensite and other things. So we'll spend a lot of time sort of looking and gaining an understanding of what we see. Okay. So there's a lot of slides here that are primarily for reference, right? This is just basically how we classify steel, and what are the main descriptors, right? So in terms of composition, generally carbon steel, low alloy, stainless, advanced high strength, low alloy, high alloy, right? We just basically have a whole bunch. How they were made, finishing, the form, the microstructure, heat treatment, quality. All of these go into different classification schemes. Most of these, most of these are here for basically just for reference, right? It doesn't make a lot of sense to just go through and list these. One example, though, that want to keep in mind with steels is aluminum had sort of an international standard designation numbering scheme. Unfortunately, steel doesn't, right? So 4140, really important automotive steel, right? There's actually 22 different international standards that all specify the same steel, right? So we have the German, the Japanese, the British, the French, right? And even within here, there's multiple other steels that that meet the classification range with sort of minor differences that would all qualify under the definition of 4140, right? So there's big handbooks of basically cross-referencing all the different specifications. and keeping track of what's what. Right, and we will refer back to this a couple times as we go through. But I put it up front here mainly for your reference, so you have a convenient spot to look for these. All right. Okay. Okay. Now we move on to so this first part is all about the growth of ferrite, right? So under sort of equilibrium things, right? So which come phases that we can read right from the phase diagram, we're going to have growth of ferrite, growth of perlite, and then we'll talk about bainite. Then we'll go on to twinning and martensite, because those are very closely related, and then into heat treatment of steels, right? So we'll go through the basics of what's happening within the microstructure, then talk about how do we optimize our processing to get what we want out of them. Okay. So basically just the key points that we want to keep in mind here: the eutectoid composition, 0.76 weight percent, right? We want to keep the eutectic in mind out here, although it doesn't come up too much. And then, as I said, we've got this paratectic point up here, which we can basically ignore, except for we're going to get some coring effects, right, from alloys that go down, because now we have a inhomogeneous austenite if we cool through the paratectic point fast enough, right? But that's sort of like a second order thing, and we don't really need to worry about it too much. Okay, so all compositions that contain less than 2.11% carbon pass through the austenite region on cooling from liquid, and we're going to arbitrarily classify these as steels. But remember, most of the time we're dealing with steels that are pretty close to the eutectoid composition or less, right? The only exception to this are things that are around 1.2% carbon, and these are some tool steels, steels used for razor blades, some knife, and other cutlery steels. But for the most part, the biggest tonnage is 0.2 to 0.3%, right? And this is our low carbon structural steels. And anything above 2% we're going to call cast iron, right? And these cast irons are not really simple alloys of just iron and carbon. They typically contain relatively high quantities of silicon and other alloying elements, and they're really best analyzed as ternary alloys rather than iron carbon by itself. And that's the silicon promotes the formation of graphite, and so cast irons generally, may, right? If they're gray cast irons, they have both graphite and cementite. White cast irons are cementite only. but that's it on cast irons until the end of the semester. Right. So for the most part, we're going to be considering things that are near the eutectoid, and for this first part, we're considering, when I say equilibrium structures or metastable structures, we're considering what happens when a steel is slowly cooled from the austenite region, right? And it's going to depend largely on the carbon composition of the steel, right? Again, if we're less than the eutectoid composition, we're going to have pro-eutectoid ferrite and pearlite. If we're at the eutectoid, we're only going to have pearlite. If we're hyper-eutectoid, we're going to have pro-eutectoid cementite and pearlite. So just images of hypo, right? The ferrite is white, the pearlite is mottled. Here we're hyper-eutectoid, so we have pro-eutectoid cementite that forms on the prior austenite grain boundaries with pearlite that grows into it. Okay, so in terms of ferrite, this first part we're interested in these regions. So first we're going to talk about reconstructive, and then a little bit into displacive with Wittgenstein, right? Okay. So as we're cooling slowly, whether we're hypo or hyper, the pro-eutectoid ferrite and the pro-eutectoid cementite are going to nucleate preferentially and heterogeneously on the austenite grain boundaries, right? And this is, right, just our grain boundaries contain energetically favorable sites for nucleation. We have higher diffusion rates because we can utilize grain boundary diffusion, right? And importantly, when the ferrite nucleates at the grain boundary, it develops a preferential orientation relationship, right? And that's the Kurgyumov-Sachs relationship, and it forms this with one of the two neighboring austenite grains, right? It can't have a preferential relationship with both grains, right? So it ends up with one of them, and it will grow into the other. So what is this Kurgyumov-Sachs looks like? So we have the 1-1-1 plane on the austenite is parallel with the 1-0-0 in the BCC, right? So sketch the atom positions in here on the plane, right, and see how they line up, right? And then the directions that are parallel are the 0-1-1 and the 1-1-1 type directions, right? So if we think about this, right, we basically, what are the slip systems in FCC? Right? The 1-1-1 planes in the close packed directions, which is 0-1-1, right? So Kurgyumov-Sachs is aligning the most close packed directions in our crystals up together, right? That's the basic physics behind the Kurgyumov-Sachs, right? So this Kurgyumov-Sachs habit plane is 111, and the ferrite nucleus aligns with the 111 direction in ferrite aligns with the 110 direction in austenite, and this habit plane forms a low energy boundary, right? It doesn't move, right? It has virtually no mobility. So that means the ferrite grain is then going to grow into only one of the austenite grains, right? And then the boundary that is created between the ferrite nucleus and this austenite grain is going to be a general high angle incoherent boundary, right? It has lots of mobility, right? So yeah, I get my, every time I say electromorphic, I get my tongue tied. So, but anyway, electromorphic ferrite grows on the grain boundary, right? And it has a shape which doesn't reflect any internal crystal symmetry. It forms at the grain boundary and follows the grain boundary contours, right? Idiomorphic ferrite, on the other hand, nucleates heterogeneously within the interior of the grain. It nucleates from non-metallic inclusions that are present in the steel, but it adopts a faceted shape, right? That's representative of the crystal, right? So the edges of the idiomorphic ferrite are low energy crystal growth directions, right? And so when we look at these in micrographs, we see here at the grain boundary, these are the allotropomorphs, right? And here we see idiomorphs within the interior of the grain, right? These are both formed by true diffusional transformation, right? There's no atomic correspondence between the parent and the product crystals, right? Meaning, other than the Kurgyumov-Sachs boundary at the grain boundary, right? When the ferrite grows in, right, it doesn't maintain any kind of orientation. There's no invariant plane strain shape change like there is for Widmanstätten or martensite or bainite, and the growth rate is going to be controlled by classical mechanisms, right? Either diffusion, right? How fast can we move the carbon out? Or interface, how mobile is our interface, or is it going to be some mix of both, right? Because it's diffusional, we need high temperatures, right? We need thermal activation, right? So this doesn't this only happens at temperatures that are close to the eutectoid temperature, right? And the interface is, that's a little confusing. The interface need not be docile. The interface in general is a general high angle interface, right? And it's not conservative. We also have partitioning, right? The ferrite is a different chemical composition from the austenite, right? So if we assume for right now, in the analysis that we're going to do, if we assume that the growth of the ferrite is controlled by the diffusion of carbon ahead of the interface, right? So as we grow, are we absorbing carbon or are we rejecting carbon? We're rejecting, right? So we've got a constant, we're pushing essentially a carbon front out in front of the interface, right? And as the ferrite grows, the extent of this diffusion field is going to become larger, right? And this has the effect of retarding the growth with time, because the solute has to diffuse over larger distances, right? It has to get farther away. We have to push more carbon farther away before we can get down to the ferrite carbon content, right? And this, we'll go through a simple analysis, but this leads to square root time dependence on the growth of the ferrite, right? So the growth rate slows down as the time increases, right? And that's really the main thing. The analysis is just sort of how we get there, right? So here's what our right, partitioning, basically this is just the lever rule. Oh, got cut off somehow. There we go. Right. So basically, at a given temperature, we're partitioned by the lever rule. This is the textbook point down here, right? So this is the concentration of carbon in our alpha, concentration of carbon in our austenite, and we assume that the profile is going to look like this linearly. Here's our interface. So out in front of the interface, we have a higher carbon content. This is the carbon content of the equilibrium, right? So this is, yeah. Oh, geez, sorry.